Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you can find information about online seminars and study manuals for exams PFM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help ISU actuary. Here's a problem for today for exam IFM. Assume the Black-Scholes framework. Consider 1 year at the money European put option on a non-dividend paying stock. You are given that the ratio of the put option price to the stock price is less than 0.049. Delta of the put option is negative 0.4364. The continuously compounded risk-free interest rate is 1.2%. Determine the stock's volatility. And here's the solution. The Black-Scholes formula tells us that the price of the put is k e to the minus rt, the present value of exercise price, times n of minus d2, minus the ex-dividend or prepaid forward price of the stock times n of minus d1. But we are told that the option is at the money, which means that k is equal to s. The continuously compounded risk-free interest rate is 1.2%, t is equal to 1, and time until expiration of the option, and that the dividend rate is delta equal to 0. Therefore, the price of the put is k times e to the minus 0.012 times n of minus d2 minus s times n of minus d1. But s is equal to k, so we can just write this as k e to the minus 0.012 times n of minus d2 minus k times n of minus d1. The delta of the put option is e to the minus delta t times n of minus d1, but here delta is 0, so that n of minus d1, the delta is the delta of the put option, and that's known to be 0.4364. This gives 1 minus n of d1 to be 0.4364, and n of d1 is 0.5636, and from the table d1 is 0.16. But d1 is equal to ln of s e to the minus delta t over k e to the minus rt plus 1/2 sigma squared t over sigma square root of t, and of course d2 is the same thing but with minus 1/2 sigma squared t, which is the same as d1 minus sigma square root of t. Okay, but then this implies that d2 has to be equal to negative 0.012 minus 1/2 sigma squared over sigma, and that is equal to delta 1, which is 0.16, minus sigma square root of t, and t is 1. So this is got to be equal to 0.16 minus sigma. So two ways we write delta 2 based on d1 to be 0.16 minus sigma, but also based on the standard Black-Scholes formula, that's 0.012 minus 1/2 sigma squared over sigma. This gives 0.012 minus 1/2 sigma squared to be equal to 0.16 sigma minus sigma squared, or sigma squared minus 0.32 sigma plus 0.024 equal to 0. This is a quadratic equation. We solve it using the quadratic formula and obtain sigma to be either 0.12 or 0.20. And based on this, we would have two possible values of d2. One is 0.04 and the other one is negative 0.04. And the corresponding values from the table, n of 0.04 to be 0.5160 and n of minus 0.04 to be 0.4840. We are also told that 0.048 is greater than p over s, and that's equal to e to the minus 0.012 times n of minus d2 minus n of minus d1 from the formula for the value of the put. So this is the ratio of the put value to the stock price, and we know that it's less than 0.048. And that's equal to e to the minus 0.012 times n of minus d2 minus 0.4364. And this gives n of minus d2 to be less than e to the minus 0.012 times 0.049 plus 0.4364, which is approximately 0.4913. Therefore, n of d2 is greater than 1 minus that, which is 0.5087. Since n of minus 0.04 is 0.4840, which is less than 0.5087, the solution is d2 equal to 0.04 and sigma equal to 0.12. That's answer A. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.